Hey, welcome back. This video is a kind of continuation on the previous videos that we've done where we've been really looking at the bytecode that's generated in JavaScript underneath the hood. So I thought it would be interesting. In the previous videos, we were just doing sort of adding numbers together and we got fairly comfortable with that. And if you want to understand what happens under the hood, then look in the top right-hand corner, click on the video, and then you can get a replay of those videos. But what I thought we would do in this case is we would look at the bytecode and how it's different for the various scopes that we have. So we're going to still stick with numbers, but we're going to look at constants, we're going to look at lets, and we're going to look at vars. And then we're going to muck around with the scopes a little bit within the scope of context, and we'll have a look at how this changes from a bytecode perspective. So I'm going to go back to my screen for a second. We're going to do what we did before. We're going to create a function called add2numbers. So we'll say add2numbers. And we will just create a constant, which is n1, and we'll set that equal to 10. And then we'll create a new constant called n2, and we'll set that to 20. And then we will return n1 plus n2. And then, of course, what we're going to do is we'll just log that out to the console. So all I'm going to do is call add2numbers, and then we can go to my terminal. Let's clear my screen, and we will run node example.jas, which is the file that I created, and you will see it returns 30, which makes sense, right? Which is 10 plus 20, and that's going to return 30. Now, if I look at just as a recap of the bytecode for a second, so if you haven't seen the previous videos, how you get access to the bytecode is you run node, and then you put in the flag --print -bytecode, and then what you want to do is filter out by the name of the function you want to look at. So in this case, it's add2numbers, and then you'll run the name of the file. So if we return that, it'll come back with the bytecode. And again, I'm going to do this really quickly. I'm sure you'll have seen this before in the other videos if you want a deep dive, but we're going to do this on paper really quickly, and then we will look at how this changes when I start changing from constants to less to vars and start changing it. So first thing is we have this, let's draw a table on my iPad. So the first thing I'm going to do is I'm going to have a column called instruction. So here is my instruction column. And we'll explain this as we go along. We've got this thing called the accumulator. Again, for a deep dive on that, please see one of the other videos. And then in this case, I've got two registers, which is register 0 and register 1. Again, if you want a deep dive on that, see one of the other videos. But I'll explain this as we go along. So if we look at the codes there for a second, you can see what's happening is load into the accumulator small integer value 10. So let's just put that in my instructions, LDA, SAMI, and its value 10. Accumulator is not going to have anything, it's now going to be loaded into the accumulator, which is 10, so we're good. So we've just loaded that. The next thing we're going to do is we're going to store, that's what star stands for, so, or the ST part is store whatever is in the accumulator, that's the R, and then the 0 into register 0. So we've got 10 in the accumulator just now, and because it's a store, whatever's in the accumulator 10, it's going to put that in register 0. So that's stored there. And then the next thing that's going to happen is it's going to do an LDA SMI, so we're loading another small integer, this time it's 20. That is going to be loaded into the accumulator. We'll keep that there. And then the next thing that happens is that, and of course our register 0 doesn't change at all, it's still 10. So the next thing that happens is, you see from the code here, it's going to store whatever's in the accumulator into register 1. So ST for store whatever's in the accumulator, that's A, into R1. 20 is in the accumulator just now. We'll keep 20 in the accumulator. 10 is still in R0, but we're going to take 20 and we're going to store it in R1. So that's going to be over there now. And then eventually we've got this function, which is add. So it's going to take whatever is in R0, which is at this point in time is 10. And then it's going to take that 10 and it's going to add it to whatever is in the accumulator. That's what add does. So add takes whatever's in that register, R0, and adds it into an accumulator. So 10 plus 20 is 30. And then, of course, the return function the return opcode then returns whatever is in the accumulator back. So our function will return 30 in this case. So that's how it works. Reset. Okay, so let's see what happens when we change the const to let. So let, and we'll hit save. And then if I run example.js, you see it's returning 30. But let's see what happens when we generate the bytecode. Let's have a look at this. Oh my goodness, it's the exact same. The bytecode hasn't changed at all. It's still loading small integer. It's still storing in registry 0. It's loading small integer again and storing in register 1. It's reloading registry 1 into the accumulator. It's adding whatever's in the accumulator, with R0, and it's returning it. So that's our first discovery. Const and let, from that perspective, from a bytecode perspective, is the exact same code. Exact same. It's not any different in this particular instance. So there isn't an advantage. There may be a bit of an advantage on parsing, right? Because it's going to create that abstract syntax tree, as I said before. But when it gets converted down into bytecode, it's going to remain the exact same at that point. So it's just something to be aware of there. If you're thinking this is some sort of performance optimization, not really. It's not going to make any sort of difference. Now, it does get a little bit interesting, though, when we start to look at some of the fun scenarios that you can get with scope. So let's come back to VS Code for a second. Let's create a couple of the weird examples that you get with, with scope, etc. So let's create n1 is equal to 20, as we did before. We'll do it let n2. I'm not going to set a value for this. And then we're going to say let result equals n1 plus n2. Actually, let's for fun, let's take the n2 and put it after the result. And then what we're going to do is return n1 plus n2. So if I run that, I'm going to get an exception thrown up, as you're going to see in a second. So reference cannot access n2 before initialization. Makes complete sense, right? I have not initialized n2, and I can't use it until it's been declared. So let's have a look at the bytecode for a second on that. So let's do print bytecode, and we can have a look at what's going on underneath. So it gets really interesting. So you've got this thing called load into the accumulator the whole, right? And this is sort of a bit of magic that is created by the V8 engine, by Ignite in that sense. But what's going on is that the accumulator's got to have a value. So this thing called the whole, it's something that should never happen. It should never exist. So it's loaded into the accumulator. So in this case, it's representing. So if we go back to our code, that's really representing what's going on with N2, right? So N2, because we have to have every declaration of a register and variable part of a function, it's got to be there, right? But it can't be undefined, right? Because it's not sitting at the top. It's not been initialized yet. So we need to put something in there. And that's how the V8 engine understands that. What it does is to handle that scenario, it calls it the whole, right? And then if there's something in the whole, then it's going to throw an error. So we can kind of see this. So in the accumulator is, in fact, let's draw it out on my iPad, right? So let's do this. So what we will do is we will have our instructions again. And what we'll have in this case is the accumulator. So we'll have R0 to represent register 0. And we will also have R1. And I think there's 3 registers in there. So we'll have R2 as well, R1 and R2. So the first instruction is LDA the whole, right? So what's going to happen in the accumulator is going to load into the accumulator this thing called the whole. Okay, so we have the whole in there. R0 is not going to have anything. R1, R2 is not going to have anything. And then it's going to run store whatever's in the accumulator into register 2. So at the moment we have the whole in there. And then so R2 is going to have the whole also. Okay, cool. So the next thing is load into the accumulator the value 20. So we'll do that. Load accumulator, small integer, and it's going to be 20. So the accumulator is now 20. And then the next call is store in register 0, the whatever's in the accumulator. So that's going to be 20. We still have the hole in R2. Yeah. R1 doesn't have anything at this point. And then what it's going to do is load back into the accumulator whatever is in R2. So the hole is in R2. So let's put the hole in there. So the hole is there. Yep. And then the next instruction is going to be throw a reference error if hole. Yep. Well, the hole is in there, right? We know this. So it throws a reference error, and that's what happens. So that's how underneath the hood, the V8 engine handles lets and const, and the fact that you can't access those variables until they've been initialized. And the trick is that, of course, in the V8 engine, every declaration that you make, whether it's let, var, or const, has got to have a register associated with it, right? It's got to be declared within that function. We've seen that, right? But we can't put undefined, because if we put an undefined in there, it's going to behave like a var. So how it handles it under the hood is it puts this value, the hole, in there, and then it does a check on the hole to see if it's in the hole, and then it throws an error. And that's how it differentiates between the two. And we can kind of see this. So if I go back to VS Code for a second, and we change these lets, so that let n2, if I change that let n2 to a var, yeah, then what's going to happen is it's going to become valid JavaScript code, right? Because the var is going to get hoisted, right? So it's that variable declaration is going to move up to the top. So that means that var n2 would actually, even though it sits below that let result equals n1 plus n2, even though it sits below that, it's going to move up. It's going to be hoisted to the top of that function, and therefore it's going to have the value undefined. And therefore the result will be n1 plus n2. So it'll be undefined plus 20, and then it's going to return not a number. So if I go back to my terminal and we run that again, note example, you see it's returning not a number, as I said. So if we look at the bytecode that's been generated now, you can see all this stuff about holes and things is gone, right? So now we're back into a sort of clean looking code, right? So we're loading into the accumulator 20, and then we're storing that 20 in register 0. And then what we're going to do is load into the accumulator whatever is in register R2. So we haven't put anything in register R2. We haven't done any loads in there. There's nothing in there, right? But we're loading whatever's in R2, and that's because R2 register 2 is assigned, right? It's set to whatever our n2 was. Now, of course, we haven't put a value in there because it was being hoisted. So there's actually a really interesting thing. That means that for registers, if you haven't put anything in there, it's going to be setting that value to undefined. We know that, right? Because we know it's going to do an undefined later on because it's going to return a not a number. So in this case, R2 is going to be undefined, and therefore in the accumulator we've now just loaded undefined into the accumulator. So now if I add R0, add whatever's in the accumulator to R0, so 20 plus undefined, then I'm going to store that in register 1. And then I'm going to load what's in register 2, add it, and return it all the way through. And it's a little bit complicated, but actually we might as well just draw it out again, right? Let's decomplicate this. So let's go to the iPad, and we're going to have instruction, and we're going to have the accumulator again, and we're going to have R0, R1, and R2. And let's just walk it through in paper, right? So the first thing is we're going to do a load of SMI 20. So we're going to load 20 into the accumulator. So that's starting. And then we're going to store whatever is in the accumulator in register 0. So let's put 20 in register 0. Next thing that we're going to do is load into the accumulator whatever's in R2. So R2 hasn't got anything in that, so let's put that eldar R2. Now, as I said before, we know that's going to be undefined, so let's put undefined. Yep. We're still going to have 20 in R0. And then we're going to add whatever is in R0 to the accumulator. So let's run that. So add R0. So undefined is in there. 20 plus undefined is undefined. Yep. And then we're going to store whatever is in the accumulator into register 1. So we know undefined is in the accumulator. And therefore, we still have 20 here. We still have 20 in here. So we're now going to store undefined in register 1. So undefined. Yep. And then we're going to load whatever's in register 2. So ldar R2, which is undefined. And we're going to load that into the accumulator. And then we're going to add whatever's in R0 onto that. So we know 20 is in R0. So, yep. So we're still going to end up with undefined. And then we're going to add whatever is in R0 to the accumulator. So that's undefined. Yep. And then we're going to return undefined. And it works. So that is how hoisting works and how constant and lets are handled for when something is not initialized. Okay, now let's finish this up. So let's come back to what we had before. So we're just going to have a const n1 equals 10, and we're going to have a const n2 equals 20. So we're back to kind of where we were, return n1 plus n2. But what we're going to now do is put a new scope within there. So let's put a scope set of brackets there, and then maybe we're going to do some other calculations. So let's say const n1 equals 30 and const n2 equals 40, and then maybe I'm going to have a new value called called result, and that is going to be n1 plus n2. Now, of course, I can do that because this is a brand new scope, right? So I can put that to 30 and that equal to 40. And unlike with a var, whatever I do in here is not going to affect up here, right? That's going to remain the same. And you can kind of, if I was to just put a console.log result here, and let's put a sort of console.log result here. And then actually, why don't we put a result here, and then we'll put const result n1 plus n2. Okay, so outside of this block scope, what you're going to see is 10 and 20, and that would be result would be 30. That will come back as 30, but within this scope here, then you would see that would become 70. So I would expect to see 70, and then I would expect to see 30. So if I go back to my terminal, just run that for a second, we'll run node, and you can see 70, 30, 30, right? That's exactly what I would expect to see. So what I'm going to do is get rid of the console logs for a second. Yeah, so what I want to look at is what happens in the bytecode. How does the virtual machine handle this block scope down here underneath? Let's take a look. So if I run nodeexample.js, it's coming back with 30, which you would expect. Let's look at the bytecode. So the first thing I want to get across here is you see the register count is 6. And then you can see all this load SMI *1 or load SMI store. Here's the key thing. As far as the virtual machine is concerned, as far as the bytecode is concerned, it cannot tell the difference, right? There is no block scope at a bytecode level. All it's doing is assigning new registers. All of that scoping is actually happening in the parsing. It's happening in the abstract syntax tree level, right? But essentially all it's doing is I've got N1 and N2 that I had before, but actually within that block, it's just creating me new registers, right? So it's you're seeing register 3 and 4 happening, you know, it's got new registers associated with it. It does the calculations, but there's no ability to access those registers outside of that scope anyway. So although we have block scopes, and although it makes sense from a parsing perspective, as far as the bytecode is concerned, there's no new scope. There's no new context. There's no new functions. None of that is happening underneath the hood. All that's essentially happening is it's creating new variables. In fact, if I were to come back to my Visual Studio Code for a second, and if I took away these blocks, and then let's say I call this n11, n21, and result1, and then put n1 plus n21, and then I ran this code again. So if I ran node example.js, returns 30. But if I look at the bytecode, it's returning the exact same bytecode. All it is a separate variable name, right? That's all it's done is it's created new registers. So the bytecode here and the bytecode there is identical. So this concept of block scoping is cool, right? But there's no new execution context. There's nothing like that. It's literally a little bit of magic in the parsing. So it's figuring out what's going on, but then it's generating new variable declarations. And of course, in your code, you can't access them. They're all internal. There's no way of accessing those registers. So you've still got that protection that you need, but underneath the hood there, it's just more registers. So that's kind of, I think, if anything, this sort of sums up why it's really important to be able to look at the bytecode, because actually you are seeing underneath the hood on what actually is happening, right? You're not making up how you think it's happening. You are seeing actually what the code is, and the code is the single source of the truth, right? So you kind of see it there. Hopefully that makes sense. Anyway, I hope this has been useful. I hope this gives you a deeper understanding of how scoping works and how block scopes work and compared to function scopes, and how const and vars and lets are handled at a bytecode level. And when you're writing your code in JavaScript, you're going to understand exactly what's going on underneath there, and it will help you make sense. Anyway, speak soon in the next video. Thanks.